This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. Got with me Chuck Nice, co-host.
Hey, what's happening, Neil?
Today we're going to do some explaining. It's explaining front to back.
Right.
Three segments that's become its own genre.
Yeah, it is. Every time you say we're going to do some explaining, I almost want to look over my shoulder for my wife.
Because of I Love Lucy?
Yeah, exactly. That's where it normally,
Okay. So this, I guess, I don't know if we settled on a title. It's stuff you thought you knew.
Okay, I like it.
Even stuff you never knew that you didn't know. So that's
I like that as a title too.
Yeah, stuff you never knew that you never knew.
Yeah, and so you never knew.
3 segments. We're going to talk about what we really mean by temperature.
Aha.
Okay. Second, we're talking about size and wavelength.
Right on.
There's stuff happening there I don't think you knew that you knew or didn't know that you didn't know. And
well, if we're talking about that, I know I didn't know.
Okay.
So.
All right. And it'll make you look twice at your microwave oven. Make sure it's designed properly.
Okay.
And third, we're going to talk about horsepower and how completely irrelevant it is when applied to rocket engines. As NASA has done for decades. So
Makes
that's
sense.
on this edition on StarTalk, Stuff You Thought You Knew. So we've talked a little bit about temperature before.
Yes.
But I just want to just sort of do it again. But
all right.
I think 10 minutes just isn't enough time to say everything you need to say. So,
about temperature, we're still talking.
About temperature, that's correct.
Okay.
That's correct. So let me first tell you, in the world of physics, what temperature is. Okay.
Oh, okay.
Temperature only has meaning when you have an ensemble of particles that are vibrating.
Okay.
So you can ask, how fast is everything vibrating?
Mm-hmm.
Okay. And you get, how fast is this one, and all sort of moving in different directions, like the molecules in a gas cloud, or even in a solid object, the particles are vibrating. Okay?
Right.
And you can ask, what is the average kinetic energy of this motion of all those particles?
So, okay, let me just ask then. Do those vibrations from these particles produce some type of measurable energy like heat?
Yeah, so they bang up against your thermometer, and then the thermometer gives you a reading.
Oh,
okay.
That's kind of dope.
I'm
liking it so far.
That's okay. So we're clean on that, right?
Yes, yeah.
No problem. Okay. So what happens if you don't have any particles?
You should be really chilly. Like you need a cup of tea.
It means you're chilling.
Yeah.
You're so chilling.
Yeah,
no. And how do you measure the temperature of something
if you don't have a vibration?
Particles vibrating against it. So what happens in that case is, because the vibrating molecules or particles are not the only thing that can put energy to your thermometer.
Okay.
All right. Light can do the same thing too, or electromagnetic energy, which includes light.
Right.
Okay. Visible light. Okay. So light goes to your thermometer as well. All right. But your thermometer has to be able to absorb it in order to then get a temperature for you.
Okay.
All right. If you're trying to find the temperature of the visible light in this room, and your thermometer is made of transparent glass, the visible light goes right through the glass, and you won't get the temperature of that light.
Okay.
So temperature is not a completely obvious thing under certain circumstances that are not even much of a stretch. Okay, so I'll give you another example. I once calculated, dare I say famously calculated, how long it would take to cook a 16-inch pepperoni pizza on the windowsill of your home on the planet Venus.
Okay, is this gluten-free we're talking? And did you make that calculation?
I didn't do the gluten factor.
Okay.
The gluten correction I didn't make. All
right.
So here's what happens. The atmosphere in Venus has like 100 times as many particles in it per volume. So it's 100 times as dense.
Oh.
So there you have your pizza in the oven, and there's hot air hitting it, but I have 100 times as much hot air hitting it. Okay?
All of Venus is one big convection oven.
Pizza oven, right? So there it is. All right, and the air is hotter. Okay? The air is like 900 degrees Fahrenheit. So and a pizza oven's only around 500 degrees Fahrenheit. So what you have 100 times the atmospheric contact and 500 more Fahrenheit degrees to boot. So I calculate if it takes 15 minutes to cook a pizza and you do the fractions and you do this right. I did it. I got about 7 seconds, between 7 and 9 seconds to cook a pepperoni pizza.
Well, no, and we'll be there in 30 minutes or less, guaranteed, baby. Guaranteed.
Well, yeah, there's between 7 and 9 seconds, around there. So then, as I've told you before, the geek spectrum knows no limits in who occupies it. All right, as I say that all the time when our good friend Charles Lewis
aboard, right?
So I put this out there, and somebody called me out and said, Dr. Tyson, you neglected the radiant energy just from the gas being hot. That's in addition to the molecular contact energy that's going on at the pizza surface. And if you included that, the pizza gets cooked in like 2 or 3 seconds.
Right.
Not the 7 seconds. So it's not only the transfer of heat from the vibrating molecules, there's the infrared light that's coming out of the warm oven. Not only the air itself, but the walls of the cavity. That's why pizza ovens are brick ovens, because the ideal ones, because the oven is radiating to the pizza on top of the air.
Yeah, everything around it is hot, not just the air.
Everything around it is hot. So so the pizza is gaining energy from the air molecules directly, and from the walls of the oven indirectly, because of the radiant influx of infrared in that case. Okay, so there's these two ways. So if you have a thermometer in the vacuum of space, what matters is how much of the photons of light is the thermometer absorbing. So if you wrap the thermometer in reflective mylar, then the temperature will just keep dropping until it reaches the temperature of the whole universe, which is damn near 0 degrees Kelvins, absolute zero. So the temperature has to do with what are you wearing? Oh, wait a minute. We've heard this before.
I'm sorry. I thought we were doing that thing. Well, Chuck, what are you wearing?
What are you wearing? No, it's who are you wearing, Chuck? Yes.
Right. Oh, yeah, okay. I forgot. Yeah, that's the red carpet way.
Did you wear it well? So when they say wear lighter clothes in the summer, what they're saying is the air will have whatever temperature it does, but you don't want to, and it's going to be hot probably, but you don't want to add to that by absorbing light from the sun, because that will just add more temperature.
That's why in the summertime, I just wear bike reflectors.
If you do that,
I just walk around with bike reflectors on.
That's all you'll get. If you just clad your body with bicycle reflectors, or something that is good at reflecting sunlight, which could just be, by the way, it's been rumored that, all futuristic sci-fi space things that people wear, they're always reflective. You have silver.
They're always silver.
It could be because they're living too close to their host star and they have to keep reflecting it off to stay cool. Point is, you cannot speak singularly about the temperature of the air in any way that matters to you if you're also exposed to light that could be absorbed by what you're wearing. So in the winter, it's cold out. You want as much extra energy as you can get. So wear dark clothes. The dark clothes absorb sunlight, and then the temperature inside your clothes goes higher than would otherwise be if you were just measuring the air.
Right.
So
and that is why in the wintertime, I hang out with my black friends, and in the summertime, I hang out with my white friends. And I'm always in the
right
Goldilocks. I'm in the Goldilocks spot always.
And in the fall and winter, you say, "Oh, can you back up a little? Come a little." No, you move away.
Exactly.
You got the zone.
In the fall and spring, I just hang out with Puerto Ricans. So.
Man, Chuck is going to get this show canceled as fast as...
Come on, people. Y'all can't get mad at that. Come on.
That was pretty funny. That was good. So I'm just saying temperature is just a little more complicated than you might otherwise think.
Right.
That's all. It's not just what is the air. It's how fast are your molecules vibrating and what is causing that to vibrate. And the air is how we usually think about it, but other things can make that happen as well. So that's what I'm saying. And there are rules about the thermometer that gives you the official weather service temperature. That thermometer is in a shadow. It's not open to the sunlight.
Ah.
Okay. In fact, I used to do this when I was growing up. I think they've corrected this. So the bank temperature time signs, they used to be on all banks.
I remember time and temperature.
Time and temperature, right? I would look at bank time and temperatures that were in sunlight and bank time and temperatures that were in shade. And the official air temperature might be 90 degrees. The bank thermometer would say 105 degrees. It's like, no, it's not, okay? Because you're sitting out in sunlight.
Right.
And you're absorbing the sun on top of the air temperature. So that misrepresents what you would feel standing in the air but in shadow, in the shadow of a tree, for example.
Gotcha.
And when you walk under a tree, say, oh, it's cooler under the tree, the air is the same temperature. So, Chuck, why is it cooler under the tree?
Well, the absence, same as the shadow temperature. It's the absence of the light being directly on you.
It's the absence of the light that you would be absorbing that would make you feel hotter. It's not just a feeling. You're actually hotter than the air temperature when you're absorbing the sunlight.
Wow. There you go. That's pretty cool, man.
Yeah, so that's just, temperature, I could go on and on.
There's a lot more to temperature than just a reading. That's
correct. And one thing I've said in multiple shows, and I'll say it again, the fact that you can see the sun in the daytime, all right, that's an obvious fact.
Right.
Means the sunlight is moving through the atmosphere, and the atmosphere is transparent to sunlight. Okay? It's a visible light, at least. So, and the visible light is where the sun's energy peaks. So if the atmosphere is transparent to the sun is not heating the air because the energy is going straight through it.
Right. Oh man. Well, there you go.
Okay. Wait. So then what does it finally hit?
At the ground.
The ground. And then the ground warms up, and then the ground is in physical contact with the air, and the ground heats the air. So, Chuck, holding aside an exotic upper layer of the atmosphere, what I'm generally telling you is, what is the hottest part of the Earth's atmosphere?
Right next to the ground.
Right next to the ground. And as you ascend, the temperature drops. As we all know, if you paid any attention at all to the data on the screen in an airplane, and what's the temperature outside the airplane? 40 below zero.
Right.
So Icarus had it all wrong.
He didn't fly too close to the... Right. His wings would have frozen. Then he would have fell.
They knew nothing about thermodynamics
right.
when they invented the story of Icarus.
That's pretty cool,
As he ascends to get close to the sun, he would have been farther away from the sun's source of heat on Earth. And the temperature would have dropped, and his wings would have frozen and cracked. He still would have fallen, but for different reasons, okay? All right, Chuck, we got to call it quits there.
That's very cool. I'm so, who knew? That was so, you always surprise me, man. You always surprise me.
That's the whole point of these.
I guess. I didn't think we could get this much out of temperature.
Temperature's a lot going on.
I didn't, who knew there was this much going on with temperature?
And let me just say, if you go high enough in the atmosphere, you reach the ozone layer.
Right.
And what does the ozone do?
Oh, it protects us from radiation and
from
harmful rays of the sun.
Okay, so to protect us, it means it absorbs it.
Nice.
Okay, so tell me about the temperature of the ozone layer.
Yes. It must be really hot.
It gets hot. And so, in fact, if you look at the temperature profile of our atmosphere, the temperature drops until you get to what we call the thermosphere, and the temperature goes back up. Because in that layer, the chemistry of the atmosphere is absorbing ultraviolet rays from the sun. And that heats that layer. And protects us down here on the surface.
That's very cool.
There you go.
There you go.
All right.
Well, the only thing I really took away from this whole thing is that on Venus, no one ever says, "Who touched the thermostat?" So,
plus, delivered in 30 minutes or less is way too long if they don't cook your pizza in 4 seconds.
Exactly. Nice.
All right. We got to take a quick break, but when we come back, we're going to talk about size and wavelength.
Okay.
These are two things you don't normally hear in the same sentence.
This is true.
We're going to put them together in ways that maybe you never thought of before. Welcome back to StarTalk, things you thought you knew. Chuck, you may have heard of the wave-particle duality.
Yes. Light.
That? Yeah. Is it a wave or is it a particle? And
hey, you got wave in my particle. Hey, you got particle in my wave.
If you're over 60, you'll get that reference to a TV commercial.
Yeah.
For Reese's peanut butter cup.
Reese's peanut butter.
So the problem is we have a brain that wants to compartmentalize.
Okay.
And doesn't really blend to what feels like disparate bits of information. So people tried. They invented the word wavicle. I thought that was pretty cool. Never caught on.
Wavicle.
Have you ever heard wavicle? Yeah. Because
it doesn't work. That's why.
It doesn't work. But let me just give some interesting examples.
Wavicle. Okay. It actually sounds like something the professor from The Simpsons, wavicle, Haven, Flavin. Okay. I'm sorry. Go ahead.
All right. So before we pick up wavicle, let me just remind you that light, which in my field we call the electromagnetic spectrum, is all forms of light. The most familiar to us is visible light. Okay, red, orange, yellow, green, blue, violet.
Okay.
But if you go on the other side of red, you get to what?
Infrared.
Infrared, very nice. Your retina can't detect it, but it exists.
Right.
We do have infrared sensors. We detect it on our skin as heat. All right, so we can detect infrared, but we don't see it. We feel it, though.
That, by the way, makes us sound so much cooler than we really are.
Oh, with our skin sensors.
We've got infrared sensors.
Yes. Okay, now you go beyond the violet, you get what?
Ultraviolet.
Ultraviolet, so that's beyond the violet. We can't see ultraviolet either. Right. We also have sensors for ultraviolet, but they're significantly time delayed.
Oh, I thought you meant like black lights that just show us all the nastiness that happened in a hotel.
Oh, no. What happens in under quote black light is you're illuminating the crime scene with ultraviolet light, which you cannot see, and certain substances fluoresce under it and send you the light back in violet light that you can see. So you're never seeing the ultraviolet.
You're never seeing the ultraviolet.
No. Okay, so here we are in ultraviolet. We have ultraviolet sensors. They're just time delayed. Okay? So the time delay is, you're out in the sun. Oh, and an hour later you feel like you have your sun. If you have lighter colored skin, you feel like you get sunburned. And you do that enough, then you get skin cancer. These are, in a way, detectors of ultraviolet. It's just too late.
Right.
Okay.
Right.
Let's go back the other end. So we had red, infrared, and you keep going in that direction on the spectrum. By the way, what's changing on the spectrum is the wavelength of the light.
Okay.
Right? So as we go to the red, wavelengths are getting bigger and bigger. We get to infrared. Beyond infrared, we get to microwaves.
Yeah.
Okay. So now I can describe the length of the wave like with physical fingers and things. So a microwave is like a few millimeters to like maybe a couple of centimeters around there.
Wow.
Just call it a centimeter. Yeah. A physical centimeter.
That's a pretty big wave.
That's a big wave. That's a half an inch. And so, full wave, a crest and a trough, gets manifested in that space when you have microwaves. Okay?
Nice. Okay.
Let's go beyond that. You get to what we call radio waves.
Right.
So before microwaves had their own name, they were just short wavelength radio waves. Okay?
Gotcha.
You've heard
Shortwave
short
radio.
Yeah. Okay. So then we said, well, there's small versions of radio waves. Let's call them microwaves, and that's why they're called micro, even though they're bigger than infrared.
Right.
All right. That's all I'm saying here. Okay. So radio waves are like meters and longer. We don't have words. A radio wave can be miles in wavelength, and we don't have a different word for that.
Wow.
So radio waves are for everything bigger than microwaves.
Wow.
All right, so now watch. If I want to detect a radio wave, I need a thing that's at least as big as one of the waves.
Gotcha.
So TV, old world TV, before it came in via cable, used antennae. Mm-hmm. How long was a TV antenna?
2 stories high.
That's right. The one on your TV
Exactly.
was about a meter long.
Right, yeah.
Okay. In fact, you'd have 2 of them.
Sticking out all over the place.
And you'd extend it to about the length of the waves of the radio waves you're trying to receive. Okay. All I'm saying is you can't detect waves bigger than the size of your detector. It doesn't work.
Okay.
Okay? It'll just wash over your detector, and your detector won't even know it happened. Right? So how about microwaves? Have you ever seen a microwave walkie-talkies? How long is the antenna on a microwave walkie-talkie? It's about like that.
That's nothing to it.
It's about
It's like an inch and a half, if
Inch
that.
and a half. There's your microwaves. That's the size of the microwaves.
That's pretty wild.
So it is the size to fit the situation.
Right.
Okay. That also means if you have a substance that prevents the transmission of any of this energy,
Okay.
you could put holes in it, and as long as the holes are smaller than the wave is not going to get through.
Whoa! That the, like...
So take a look at your microwave oven.
That's what I was about to say. That's why all the microwaves...
So microwaves go through glass, no problem.
Gotcha.
All right? So you have a glass thing, so microwaves and visible light go through, so you can see your food cooking. But there's something else on the other side. There's a screen. And that screen is opaque to microwaves, okay? Except they put holes in it.
Now that's why I got this tumor on my head.
No, you stop.
Is that why?
Don't stick your head inside the microwave oven. Yeah. So neither you nor the microwaves can see through that material except for the fact that they put holes in the material.
Right.
How big are the holes?
Tiny.
They're smaller than the size of the microwaves they're using in that oven.
That's pretty wild.
Microwaves cannot squeeze out.
It's the antenna in reverse.
In reverse. Ooh, I like that. Very clever.
Cool.
Very clever. So you can put holes in things. So radio telescopes. Have you ever seen a radio telescope? Go to a radio telescope one day. They're huge. They're huge, and they're made of like mesh. They're like chicken wire mesh with these huge holes in it, because it's depending on which kind of radio telescope you're visiting, that the metal is reflective of radio waves, but you don't have to build the whole surface of metal. You can put big holes in it, makes it lighter, all right? And rain can get through and not a problem, and because of these huge dishes, and they can take radio waves, reflect them to a focus, and there you have it.
That is really, really cool.
Well, let's keep going in the other direction.
Okay. There's more?
But wait, there's more. Okay.
I was satisfied, but yes, please continue.
So let's go the other direction. So we go red, orange, yellow, green, blue, violet, ultraviolet. You go beyond ultraviolet, you have X-rays.
X-rays.
Wavelengths are getting smaller and smaller and smaller and smaller.
Okay.
Really tiny, 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 tiny. Much smaller than the wavelengths for visible light.
Aha.
Okay? All right, so now watch. If I have a regular microscope and I want to see something small, I cannot see anything smaller than the wavelength of the violet light I'm using in the visible spectrum.
Oh, man.
Because otherwise, it washes right over it. It would not even know it's there.
Right.
Okay? So, if you want to see things smaller than the wavelength of visible light, that would be the violet side of it, you need even smaller wavelengths of light.
Interesting.
So here's talk about getting clever. You ready?
Okay.
So people said, how about electrons?
Right.
You say, well, electrons are particles. They're not waves. They're also waves. Oh my gosh. What wavelength corresponds to electrons that we could generate in a machine? X-rays.
That's
my
right.
gosh.
Yeah.
So electrons and X-rays have the same wavelength.
Wow.
So if I invent a microscope that uses electrons, then I'm using a wavelength of light as small as X-rays, so I can see the tiniest detail. So the photographs that have the most exquisite detail of the smallest things are not regular microscope photographs. They're electron microscopes. Because we commandeered electrons, piggybacked an electron using the X-ray wavelength that it represents. That's why you see those bug pictures with the hairs and the thing, and the bacteria. All of this, there you go.
That is fascinating. That's
how
electron microscopes work.
That's how they work. Isn't it clever of the human mind to do that? After quantum physics, we said we got the wave-particle duality, and I can't see anything smaller than the wavelength of violet light. But I know there's got to be detail there, because there's detail up until the point where it gets fuzzy.
Right.
Well, let me keep going. And then you invent the electron microscope, and bada bing. The world of the small continues to open to you.
So that means what's the smallest wave? Is it gamma?
Yeah. So the smallest waves that we have a word for are gamma rays. So gamma rays are the opposite, like radio waves. So it's smaller wavelengths than X-rays are gamma rays, and then we don't keep dividing it. So gamma rays that are like really, really, really small, they're still called gamma rays. Yes.
Okay, gotcha.
So the problem is, if a gamma ray telescope, you have to be able to focus it.
Okay.
It's not good enough just to use the light. You need to be clever about when the machine you're making, and we know how to focus electrons because they have a charge.
Right.
And so we can focus them down and get images and things. So, yeah.
So the only thing gamma rays are good for is making you a superhero.
A Hulk, yeah.
Yeah.
That's tested. We know.
Right. We know that.
And I think it's gamma rays on Spider-Man too.
I don't know. I'm not sure what it is. But
well, there was a radioactive spider.
It was a radioactive spider that bit him.
And
I'm not sure what kind of the machine was using to make him.
Yeah.
You know. First of all, I just love that we went from pure science. Here's how an electron microscope works to now exactly how the Spider-Man.
And this is how you become the Hulk.
And this is how you become the Hulk.
In your basement. So all I'm saying is check your microwave oven. If your holes are the size of like a centimeter, they're too big and microwaves are leaking out.
Right.
If they're down around a millimeter or two, then that's a good size. You're not getting the microwaves are not getting out.
There you go. There you go. You don't want to end up with a tumor on your head like Chuck Nice. See?
What do you do? Why that TMI? So what's going on your forehead?
Oh, I had a concussion some time ago, and I have to get this surgically removed. So it's there now, and it won't go away.
Okay, all right.
And my wife did it.
Okay.
I may have buried the lead, but
it's all right. So that's a little bit on size and wavelengths that you might not have known, a connection that you might not have known was ever there.
That was great.
All right, Chuck, we got to take a quick break, but when we come back, all kinds of stuff you never knew about horsepower.
Oh, nice.
In our third segment when we return. We're back. StarTalk, things you thought you knew. Our third and final segment, all about horsepower. Chuck, I do a fair amount of reading of history. I love looking at how we used to think about things and how the advance of science and technology modifies, improves, supplants whole words, whole concepts that just become obsolete.
Yeah.
Like I think our parents might have been the generation that might have still called a refrigerator an icebox.
Which, because it was an actual icebox at one point.
Literal icebox. The Iceman would come. In fact, my mother...
Get your ice here! Ice cold ice!
Is that how cold it is? It's ice cold. And so, Chuck, where was the space within the box where they put the ice?
Hopefully up top, since cold air falls.
Exactly, cold air falls. Chuck, you're thermodynamically fluent. I love you, man. Okay, and it would have a mechanism where it melted, and you'd replace the pan at the bottom where the water melted. Okay, so then we don't need ice for it anymore because we perfect refrigerators, and it orphans some people's vocabulary, but that's fine. I don't think anyone under 60 calls it an icebox anymore. So I find that fun to track vocabulary, the evolution of vocabulary in the face of the progress of science and technology.
You just reminded me of my great-grandmother, and I'm just having a fond memory right now because she lived until I was 30, and she was born in 1901 and used to routinely tell me about the Iceman and the fishmonger and the milkman, that all these people came around, and by the way, on horse-drawn carriage. So that's the stuff you didn't get from the market.
Right.
Somebody came by and you got it outside your door.
Especially since it was perishable or would melt, right?
Exactly.
They couldn't just leave it at the market hoping you'd come by and get it, right?
Exactly.
Right. So we go from horses, which... we built civilization on the back of horses. We also fought wars on the backs of horses.
And they never got a thank you.
They never got it. No, there's some horse memorials in the world.
Get out!
To the war horses, yes.
All right.
I was speaking with my sister about that. Also, many a war statue are the soldiers on a horse. So the horses are a fundamental part of that. But you're right. I don't think anyone told the horses before they went into battle that they'd be shot at. I'm pretty sure that was not a... we did not.
They would have bucked every soldier.
So we use horses up until the car is invented, right?
Right.
So Carl Benz sort of makes a really good version of an internal combustion engine, and we're off to the races. So then what happens to the horse? Well, the horse rapidly disappears, especially from urban centers, and then basically from all of civilization. Much later on farms, I think, but eventually they would be replaced with tractors. Okay.
Right.
So what is the power of a horse? Well, I don't know, but let's just call it 1 horsepower. Okay. So now you have a car, and what does someone who rode horses all their life call a car? A horse-drawn carriage without a horse.
A horseless carriage.
A horseless carriage, okay? Because that's the reference frame you're using to identify it. So now you say, how powerful is the engine? We don't have any way to think about the power of the engine other than in reference to horses. So car engines started getting measured in horsepower.
That makes sense.
Horsepower. Okay, it's 1 horsepower. So then I know that's like my horse.
Right.
2 horsepower. Hey.
Oh, I got a pretty nice carriage going on here.
I got carriage going on.
Yeah.
4 horsepower.
Oh, 4 horses. This is like Cinderella.
No, and 6 horsepower is Ben-Hur.
Yeah.
Okay. So there you have it. Now, So power, once we all became metrified, you can think of it in terms of watts. So 1 horsepower equals about 750 watts.
Okay.
All right. And because power doesn't have to be how fast are you moving, it's what is the rate that you are consuming energy.
Right.
So
Okay.
In the old days, hair dryers would be up around that many watts.
Yeah.
Right? Nowadays,
and
they're
they put it they put it on the hairdryer still.
well, no, watts. They don't put horsepower on a hair dryer.
No, the watts.
Yeah, yes, definitely put watts on it.
Yeah.
But I'm saying, but generally you see horsepower on things like that go into motion, or in some cases, I've seen horsepower on lawnmowers, on motorcycles, things that have sort of engines, because that's where the deepest roots are traceable to when horses did that work.
Right.
That's all I'm saying. Okay, so now we are left with the completely absurd statement in NASA press releases of how many horsepower the shuttle rocket engines are.
Oh man, I love that.
Okay.
Oh man, it's like souped up Santa Claus. 2,000 horses flying into the sky.
So you have NASA's press releases saying the shuttle main engine produces 37 million horsepower.
Oh my God.
Okay.
That is
so you
ridiculous.
say that's powerful, but it is completely meaningless.
Right.
Because
there are not 37 million horses anywhere. You will not find 37 million horses probably on Earth. Let alone all together just hanging out.
At Kennedy Space Center.
Right, exactly.
So now let's just say you could strap them together.
Right.
No matter how clever is your strapping, your 37 million horsepower is not going to, if it's actually made of horses, it's not going to put you into orbit.
No. Right.
The horses are not going to ascend from Earth and go into orbit around Earth.
However, it is kind of cool to start every space mission with 5, 4, 3, 2, yeah!
Gentlemen, start your horses.
Exactly.
So we didn't have a term that comes to us from cars that we would then apply to rockets. It would have been nice if we had car power.
Right.
Right? Leave horses behind. Now we have car. So what's car power? Let's say 100 horsepower is now 1 car power, let's say. All right. Then we could talk about rockets and car power. If we're going to be one generation behind, I would have been okay with that. But no, they kept referencing horses, which I think is completely absurd. And like I say, now, since horsepower is just a matter of power, and so are watts, and we all, in the USA, we're all watt fluent, all right? We could just use watts, kilowatts, that sort of thing. Okay? There was a similar challenge when we detonated the first atomic bomb.
Yeah.
Right? So is there a unit of energy to talk about atomic bombs? No, because no one ever made one before.
So let me guess. We now use exploding horses.
No. No. So we look back and said, what is the biggest explosion that we had before? It's
dynamite.
a stick of dynamite. Okay. And dynamite is TNT. And TNT, by the way, discovered by Alfred Nobel, got quite wealthy from it, and then created a fund to reward science and peaceful applications of it, especially with regard to medicine. So TNT, a stick of TNT dynamite, is the biggest explosion we had. So now we have an even bigger explosion, and so atomic bombs were measured with respect to how many tons of TNT it would be.
Wow.
Okay? So the 2 bombs dropped in Japan in warfare by the United States. Each of those was between 10 and 20 kilotons of TNT.
Daggone.
1020,000 tons. Kilotons, okay?
That's crazy.
So now watch. So that's a fission bomb that takes uranium and plutonium, big atoms, splits them into two lighter atoms, but those two lighter atoms, when you add them back, you don't get to the original atom. There's extra energy that got converted into the bomb, okay?
Gotcha.
All right, so we would develop an even more potent nuclear weapon called the hydrogen bomb, which comes from fusing hydrogen atoms together to make helium. So you take 4 hydrogen atoms, you get a helium atom, and you started out with more mass than you ended up. Where did the mass go? Became energy.
Energy.
E equals mc squared. All right.
Wow.
So mild hydrogen bombs are 1,000 times more powerful than your atom bombs.
Wow.
So we don't speak of them in terms of kilotons. We speak of them in terms of megatons.
Nice.
10 megatons, 50 megatons. Mega as in million.
Right.
Okay? So once again, we have these devastatingly powerful weapons, and we're referencing their power by something Alfred Nobel invented a century earlier.
Wow.
And so to me, that's the same as, well, I mean, not identically the same, but it's linguistically the same as calling a refrigerator an ice box.
Right.
And talking about the power of your car in horsepower. Right. Right. And we're still there. It's still measured in megatons.
It's still measured in megatons. Is there anything bigger than a hydrogen bomb?
Not that, well, a supernova is pretty big, but we just measure those in ergs with a power, very high power. Yeah, we stopped finding words for it. let's just go back to any unit of energy and stick in the high.
And stick it there.
Stick it there.
Gotcha.
Right. We're not measuring supernova in terms of horsepower or TNT.
Or TNT.
Right. This is not happening. You know what would be good? If we measured it, this would blend pop culture with science. If we measured it in Death Star power.
Yes.
The power it takes to completely obliterate a planet. We can calculate what that is. Oh my gosh. And then our hydrogen bombs would be, it's only 1/1,000,000th a Death Star.
That's pretty funny.
And then it becomes small rather than large.
Exactly. Yeah.
But yeah, you can calculate exactly how much energy it takes to completely obliterate a planet.
Right.
And by the way, in Star Wars The Force Awakens, where they have the new and improved Death Star, they can kill all the planets of an entire solar system.
Right.
And you know where it got its energy from?
Where?
Okay, it sucks the energy out of a nearby star.
Oh, the star. Right.
Okay, so it goes to a star, sucks out all the energy, contains it, and then dishes it out and can take out a whole solar system all at once. So that's badass, right?
That is pretty badass.
Except if you actually add up all the energy of a star, it could kill 1,000 planets, not just 10.
Oh, wow.
So they didn't do their math. Because had they, then the dark force, the dark side would have been way more powerful than anything portrayed in that movie.
You know what? We should do a show, and I don't want to offend anybody because I'm a huge Star Wars fan, but over the years, I've heard you say many, many things that Star Wars gets.
Hold me back.
That they get it, and that they get totally wrong. We should do a show called "Star Wars is Stupid." No, we should. It'd be awesome. I mean, it doesn't mean that we don't like it. It just means like, look, here's all the bad science that you find in Star Wars.
You mean like BB-8 is a smooth rolling metal spherical ball,
right?
And somehow it's not sliding uncontrollably on sand.
Or not only sand, but on waxed floors like a bowling ball. Dude, that'll be a great show. Star Wars is stupid.
Okay. How to cut your viewership in half. Right? All right, so there you have it. Just sort of orphaned vocabulary as time moves on. And yeah, it's just how culture embraces it or not. So, Chuck, we got to land this plane.
Oh, man.
Or land those horses.
Yes, I was going to say, are we on? Do we have saddles? Do we have saddles to land this plane?
Or we're gonna cut the red wire on the fuse to that bomb,
right?
And bring this episode to a close. But I enjoyed it. I enjoyed talking about stuff that people don't always know that they know.
These are fun.
Yeah, and I'd like to believe it connects you just a little more closely to the coming and going of society and all the ways that technology touches it or doesn't.
I love that.
All right. This has been StarTalk. Always good to have you, Chuck.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking up.